So let us discuss what are the demands of the semiconductor designs towards the technology where we are using 2nm technology at present, and let us check into the evolution of DFT. So basically let us know the importance of DFT first. So what is DFT? So DFT basically a set of techniques and methodologies which are integrated into the chip design to ensure that the manufactured chips can be effectively tested for the defects, and which makes it easier to detect the manufacturing faults and ensure the reliability of the finale product. And this DFT aims to improve the testability of a design even. So let us check into the what are the defects in nanometer scale chips. So, with billions of transistors packed into a single chip, so there will be the likelihood of manufacturing defects arises. So, in this context, DFT becomes very crucial because it provides the necessary infrastructure to detect these defects, ensuring that the only functional chips reach the market. So, as semiconductor technology scales down to 5nm and beyond, complexity of the chip design increases exponentially. So, without this DFT, the yield and the reliability of the advanced node chips would be severely compromised. So, this is why the DFT is critical for the nanometer scale chips. So, let us see what are the major challenges in DFT for advanced nodes like 5nm and 2nm. So the first challenge will be the higher defect density. So which gives the more defects due to complex manufacturing. So as we move to 5nm and 2nm nodes, the defect density increases due to the integrate manufacturing process. So smaller future sizes and the new materials introduce the new types of defects which are very harder to detect and diagnose. So in this position, DFT must evolve to address these new defect mechanisms and require more sophisticated test patterns in order to detect the cases and then fault modules. So this major second challenge will be the IR drop and the power integrity, which means how can the scan test cause the power issues. So basically scan testing is a common DFT technique, so which involves the shifting large amount of data through the scan chain, so which can use the significant power consumption and even the IR drop issues. So in advanced nodes, the power delivery network is more susceptible to the voltage drop, so which leads to the potential timing violations and even the functional failures during the test. So in these issues, managing power during the scan testing is definitely a critical challenge. So the next is the scan chain routing complexity. So which gives the impact on area and congestion. So the routing of scan chain becomes increasingly complex in advanced nodes due to the higher density of the logic, and which is need to be minimize the area of overhead. Congestion and the routing delays can impact the timing and the performance of the design, balancing the need for testability with the constraints of the area and routing, which is a significant challenge. So the next will be the increased test time and the cost, where we get the scaling issues in ATPG patterns. So automatic test pattern generation is used to create the test patterns that detects the manufacturing defects basically. So however, as designs grow more complex, the number of test patterns required increases. So which leads to the longer test times and even the higher cost. So scaling ATPG to handle the complexity of 5nm and 2nm designs without compromising defect coverage is a major challenge. So yield loss and the defect coverage trade-off. So which leads to the difficulties in balancing the test coverage versus yield. So achieving the high defect coverage often requires more aggressive testing, so which can lead to yield loss. So due to these false positives or over testing in advanced nodes, the trade-off between the test coverage and the yield becomes more pronounced. So the DFT strategies must carefully balance these factors to maximize the both the yield and the reliability. So the last major challenge in this DFT is the aging and the reliability. So which is the need for on-chip monitoring and BIST, so built-in self-test. So as chips operates in the field, they are subjected to aging effects which can degrade performance over time. So ensuring the long-term reliability requires on-chip monitoring and BIST capabilities. So this DFT must incorporate all the mechanisms to detect and mitigate aging related issues, adding another layer of complexity to the design. So these are the major challenges which we come across the advanced nodes like 5nm and 2nm. So let us check into the what are the innovations and solutions in this advanced DFT. So the first thing will be the hierarchical scan test architecture. So hierarchical scan test architecture, which is nothing but it allows for the more efficient testing by partitioning the design into the smaller and manageable blocks. So this approach reduces the complexity of the scan chain routing and it improves the test coverage while minimizing the area overhead. And the next one will be the AIML for test pattern optimization. So AIML are being leveraged to optimize the test patterns, so reducing the number of patterns needed while maintaining the high defect coverage. And AIML can also help in identifying and prioritizing the critical test patterns, so improving the test efficiency and reducing the test time. So the third innovation is the low power test techniques, so which gives the exfilling and the shift to power reduction. So low power test techniques such as exfilling and shift to power reduction are essential for managing the power consumption during the scan based testing. So these testings helps mitigate the IR drop issues and ensure that the chip remains within its power budget during the test until the tape out. So the last one is the adaptive testing for the yield improvement. Adaptive testing involves the dynamically adjusting test parameters, so based on the real time data from the manufacturing process. So this approach can help improve yield by identifying and compensating the process for variations, so which reduces the likelihood of the fault positives and over testing, so in which we can improve our yield. So these are the innovations and solutions for this advanced DFT. So let us see what is the future of DFT in 2nm era. So here arises a question: will DFT evolve with the AI driven defect prediction? So as we move into the 2nm era, AI driven defect prediction is likely to play a significant role in DFT. So DFT becomes more proactive, identifying and addressing the issues before they manifest into the final product. So by leveraging the AI to predict the potential defects based on the design and the process data, so sure we can tell that DFT evolve with AI driven. And what are the roles of the 3D ICs and chiplets in redefining the testing? So, testing these complex multi-die systems require new approaches to ensure that each component is fully tested and that the system has a full functions correctly. So, the emergence of 3D ICs and chiplets introduce the new challenges and opportunities for the DFT, and this DFT will lead to evolve to address the unique challenges posed by 3D ICs and chiplets, including the inter-die communication and thermal management, which is a major crisis now, and the yield optimization. So this will be the future of DFT in 2nm era. So let us conclude. So, as we look to the future, DFT will continue to evolve, incorporating the AI driven defect prediction and adapting to the complexity of 3D ICs and chiplets. So, DFT is more critical than ever in the era of 5nm and 2nm nodes, so where the complexity and the density of the chip design presents new challenges in the defect detection, power integrity, and also the yield management. So, which ensures that the next generation of the semiconductor devices meets the highest standards of quality and reliability. And innovations in hierarchical scan architectures like AIML driven test optimization and low power test techniques are essential to address these type of challenges. So this is a small presentation on the technology nodes like 5nm and 2nm, which is the effect on the DFT. So and it ensures that these DFT's technology nodes ensures that the next generation